Scientists just built an electron lighthouse that steers electrons using only light. Source: University of Michigan. Research published in Physical Review Letters. For more than a century, one of the most basic principles of electronics has remained unchanged. If you want electrons to move through a material, you apply an electric field. Every electronic device we use today, from smartphones and computers to satellites and supercomputers, depends on this simple concept. Tiny voltages push billions of electrons through microscopic circuits, carrying information from one component to another. It is the foundation upon which modern civilization has been built. But what if electricity itself was no longer required to control the motion of electrons? What if light alone could not only generate an electric current, but also decide exactly where those electrons travel? It sounds like science fiction, yet researchers at the University of Michigan have now demonstrated precisely that. Using carefully synchronized laser pulses, they have created what they call an electron lighthouse, a remarkable quantum device capable of launching a narrow beam of electrons and steering it in any chosen direction without applying an external electric field. Instead of wires telling electrons where to go, laser light becomes the navigator. Although this breakthrough is still fundamental research, scientists believe it could eventually reshape future optical communications, ultra-fast imaging systems, next-generation sensors, and entirely new forms of information processing, where electronics and photonics work together far more efficiently than ever before. To appreciate why this achievement is so remarkable, we first need to understand how conventional electronics operate. Inside every electronic circuit, electrons behave somewhat like tiny balls, rolling through an enormous maze of atoms. When a voltage is applied, an electric field pushes these electrons in a particular direction. However, their journey is far from smooth. As they travel, they constantly collide with atoms inside the material, scattering in countless random directions before gradually drifting toward their destination. This process works extremely well and has powered decades of technological progress, but it also creates unavoidable limitations. Every collision wastes energy as heat. Every electrical connection introduces resistance. Every transistor has physical speed limits. Engineers have spent decades searching for methods that allow electrons to move more efficiently, more precisely, and with less energy loss. One promising solution has been replacing electrical control with optical control using light instead of electric fields. Scientists have already shown that intense laser pulses can generate electrical currents inside certain materials. But until now, light could only act like an on and off switch. It could start the flow of electrons, but it couldn't precisely determine where those electrons would travel once they were created. The new device changes that entirely. Instead of using a single laser, the researchers employed two synchronized laser pulses of different colors. These aren't ordinary beams of light simply shining onto a semiconductor. Their colors, timing, and polarization are carefully controlled so that they interact with the material simultaneously. Polarization describes the direction in which a light wave oscillates as it moves through space. By rotating the polarization of the two laser beams, the scientists discovered they could steer the resulting stream of electrons into different directions with remarkable precision. Imagine standing on a dark coastline watching a lighthouse. As the lighthouse rotates, its beam sweeps smoothly across the horizon, illuminating different regions one after another. In this new quantum device, something remarkably similar occurs. Instead of rotating a beam of visible light, scientists rotate a narrow beam of moving electrons. By simply adjusting the properties of the incoming laser pulses, they can sweep that electron beam through different directions without ever touching the semiconductor or applying an electrical voltage. Light no longer merely creates the current, it actively aims it. The secret behind this extraordinary behavior lies deep within the strange world of quantum mechanics. In everyday life, we usually imagine a single event producing a single outcome, but quantum physics allows something much more unusual. A particle can reach the same final state through multiple different pathways at the same time. In this experiment, the semiconductor absorbs the incoming laser energy through two separate quantum absorption processes occurring simultaneously. Each laser color provides photons carrying different amounts of energy, and together they create overlapping quantum pathways, leading electrons toward identical final energy states. Because quantum mechanics describes particles as waves as well as particles, these different pathways interfere with one another much like ripples spreading across the surface of a pond. When two ripples meet perfectly in phase, they reinforce each other, producing a larger wave. When they meet out of phase, they cancel each other almost completely. The same phenomenon happens here. For electrons traveling in one particular direction, the two quantum pathways reinforce one another, greatly increasing the probability that electrons move that way. For electrons attempting to travel in other directions, the pathways interfere destructively, suppressing their motion. The result is not a broad electrical current flowing randomly through the semiconductor, but a highly focused beam of electrons traveling in a carefully selected direction. This phenomenon had actually been predicted years earlier by theoretical physicists, who proposed that such an electron lighthouse should be possible under the laws of quantum mechanics. Turning that mathematical prediction into reality, however, proved enormously challenging. Building the semiconductor device required exceptional precision because even the slightest unwanted electric field could contaminate the results. If stray electrical forces were present, researchers would no longer know whether the electrons were responding to light or to hidden electric fields inside the material. Creating a perfectly neutral structure became one of the most difficult aspects of the entire project. Doctoral researcher Yiming Gong worked closely with engineers at the University of Michigan's Lurie nanofabrication facility, experimenting with different fabrication methods, temperatures, and manufacturing techniques, until they finally produced a device clean enough to demonstrate the effect exactly as theory predicted. Only then could they confidently prove that the electrons were moving solely because of the carefully engineered laser light. Although today's demonstration was designed primarily to explore fundamental physics, its potential technological impact could be enormous. One obvious application involves optical communications. Modern communication systems increasingly rely on light traveling through fiber optic cables because photons can carry vast amounts of information at incredible speeds. However, electronic processors still need to convert those optical signals into electrical ones before computers can use them. That conversion introduces delays and consumes energy. If light could directly control electron motion inside future electronic chips, the boundary between photonics and electronics could begin disappearing. Information might flow almost seamlessly between optical and electronic systems, enabling faster communication networks and more efficient computing architectures. The same principle could also improve highly sensitive optical detectors capable of measuring subtle changes in incoming light. Future imaging systems might exploit these precisely controlled electron beams to achieve higher resolution while consuming less power. Scientists even suggest the technique could eventually help encode more information into communication signals by controlling electron flow in entirely new ways. Another exciting possibility lies in future quantum technologies. Quantum computers, quantum sensors, and advanced photonic circuits all require exceptionally precise control over the movement of electrons, photons, and other quantum particles. The ability to steer electrons purely through carefully engineered light fields could provide new methods for manipulating quantum information without relying on conventional electronic circuitry. Because the direction of the electron beam depends entirely on the properties of incoming laser pulses, future devices may be able to reconfigure themselves almost instantaneously simply by adjusting the characteristics of the light. Instead of physically redesigning hardware, engineers could alter the behavior of a device dynamically using programmable optical signals. Such flexibility could become extremely valuable as quantum technologies continue advancing over the coming decades. Of course, this discovery is still at an early stage. The Electron Lighthouse is not about to replace the billions of transistors inside today's computers or smartphones. Researchers have demonstrated a new physical phenomenon under carefully controlled laboratory conditions, not a commercial technology ready for mass production. Many engineering challenges remain before such devices could be integrated into practical electronics. Scientists will need to improve efficiency, understand how the effect behaves under different operating conditions, and determine whether it can be scaled for real-world applications. Nevertheless, history repeatedly shows that some of the most transformative technologies begin with discoveries that initially appear to have little practical use. Lasers, transistors, semiconductors, and fiber optics all started as fundamental scientific investigations before eventually reshaping the modern world. Perhaps that is the most exciting aspect of this breakthrough. For generations, electronics has depended on electric fields to direct the movement of electrons. Now, for the first time, scientists have shown that carefully engineered laser light can perform that task with extraordinary precision, creating a controllable beam of electrons that behaves almost like the rotating light from a lighthouse. It represents another reminder that quantum physics continues to reveal possibilities far beyond our everyday intuition. And if future researchers learn how to harness this phenomenon on an industrial scale, tomorrow's computers, communication systems, sensors, and quantum technologies may no longer rely solely on electricity. Instead, they may guide electrons using nothing more than the remarkable power of light itself. That electron beam through different directions without ever touching the semiconductor or applying an electrical voltage. Light no longer merely creates the current, it actively aims it. The secret behind this extraordinary behavior lies deep within the strange world of quantum mechanics. In everyday life, we usually imagine a single event producing a single outcome, but quantum physics allows something much more unusual. A particle can reach the same final state through multiple different pathways at the same time. In this experiment, the semiconductor absorbs the incoming laser energy through two separate quantum absorption processes occurring simultaneously. Each laser color provides photons carrying different amounts of energy, and together they create overlapping quantum pathways, leading electrons toward identical final energy states. Because quantum mechanics describes particles as waves as well as particles, these different pathways interfere with one another much like ripples spreading across the surface of a pond. When two ripples meet perfectly in phase, they reinforce each other, producing a larger wave. When they meet out of phase, they cancel each other almost completely. The same phenomenon happens here. For electrons traveling in one particular direction, the two quantum pathways reinforce one another, greatly increasing the probability that electrons move that way. For electrons attempting to travel in other directions, the pathways interfere destructively, suppressing their motion. The result is not a broad electrical current flowing randomly through the semiconductor, but a highly focused beam of electrons traveling in a carefully selected direction. This phenomenon actually been predicted years earlier by theoretical physicists, who proposed that such an electron lighthouse should be possible under the laws of quantum mechanics. Turning that mathematical prediction into reality, however, proved enormously challenging. Building the semiconductor device required exceptional precision because even the slightest unwanted electric field could contaminate the results. If stray electrical forces were present, researchers would no longer know whether the electrons were responding to light or to hidden electric fields inside the material. Creating a perfectly neutral structure became one of the most difficult aspects of the entire project. Doctoral researcher Yaiming Gong worked closely with engineers at the University of Michigan's Lurie nanofabrication facility, experimenting with different fabrication methods, temperatures, and manufacturing techniques, until they finally produced a device clean enough to demonstrate the effect exactly as theory predicted. Only then could they confidently prove that the electrons were moving solely because of the carefully engineered laser light. Although today's demonstration was designed primarily to explore fundamental physics, its potential technological impact could be enormous. One obvious application involves optical communications. Modern communication systems increasingly rely on light traveling through fiber optic cables because photons can carry vast amounts of information at incredible speeds. However, electronic processors still need to convert those optical signals into electrical ones before computers can use them. That conversion introduces delays and consumes energy. If light could directly control electron motion inside future electronic chips, the boundary between photonics and electronics could begin disappearing. Information might flow almost seamlessly between optical and electronic systems, enabling faster communication networks and more efficient computing architectures. The same principle could also improve highly sensitive optical detectors capable of measuring subtle changes in incoming light. Future imaging systems might exploit these precisely controlled electron beams to achieve higher resolution while consuming less power. Scientists even suggest the technique could eventually help encode more information into communication signals by controlling electron flow in entirely new ways. Another exciting possibility lies in future quantum technologies. Quantum computers, quantum sensors, and advanced photonic circuits all require exceptionally precise control over the movement of electrons, photons, and other quantum particles. The ability to steer electrons purely through carefully engineered light fields could provide new methods for manipulating quantum information without relying on conventional electronic circuitry. Because the direction of the electron beam depends entirely on the properties of incoming laser pulses, future devices may be able to reconfigure themselves almost instantaneously simply by adjusting the characteristics of the light. Instead of physically redesigning hardware, engineers could alter the behavior of a device dynamically using programmable optical signals. Such flexibility could become extremely valuable as quantum technologies continue advancing over the coming decades. Of course, this discovery is still at an early stage. The Electron Lighthouse is not about to replace the billions of transistors inside today's computers or smartphones. Researchers have demonstrated a new physical phenomenon under carefully controlled laboratory conditions, not a commercial technology ready for mass production. Many engineering challenges remain before such devices could be integrated into practical electronics. Scientists will need to improve efficiency, understand how the effect behaves under different operating conditions, and determine whether it can be scaled for real-world applications. Nevertheless, history repeatedly shows that some of the most transformative technologies begin with discoveries that initially appear to have little practical use. Lasers, transistors, semiconductors, and fiber optics all started as fundamental scientific investigations before eventually reshaping the modern world. Perhaps that is the most exciting aspect of this breakthrough. For generations, electronics has depended on electric fields to direct the movement of electrons. Now, for the first time, scientists have shown that carefully engineered laser light can perform that task with extraordinary precision, creating a controllable beam of electrons that behaves almost like the rotating light from a lighthouse. It represents another reminder that quantum physics continues to reveal possibilities far beyond our everyday intuition. And if future researchers learn how to harness this phenomenon on an industrial scale, tomorrow's computers, communication systems, sensors, and quantum technologies may no longer rely solely on electricity. Instead, they may guide electrons using nothing more than the remarkable power of light itself.